All right. So, in fact, you will be getting a lot of slides via Moodle on those subjects, and I'm not promising I will go through all the slides today. In fact, it could be that we will have some free speaking slots in the coming weeks, and then I would actually deliver some more slides. Okay. So this is kind of the overview. We're going to talk about epidemic spreading. We'll talk about network risk, about cascading effects, systemic resilience, blackouts, gas supply, energy supply altogether, and supply chains, and circular economy, if there's time. Okay, so all very recent subjects that, however, we've been working on quite a few years back. So you could ask yourself, why then do we have all these problems now if the knowledge was there already many years back? So in a sense, we had a good feeling for what would be the subjects to address. Now we're starting with the spreading of diseases. Now, as you know, one of the greatest plague in all times was the Black Death. And at the time of the Black Death, basically, the disease was spreading in a way that is shown by those lines over here. It's a pretty diffusive pattern, as you can see. This has actually changed dramatically. On the left, you'll see that diffusive pattern in a computer simulation, in that case for the country of Germany. And on the right, in comparison, we'll see a more realistic representation and see Berlin flashed up in Hamburg before actually the diffusive wave front was reaching those cities. Do you have any idea why this happens? Yes? Air transport. Absolutely. So, in fact, all this air traffic is basically spreading diseases, kind of clear, right? And people take it just with them. And that is messing up the diffusive patterns, and that makes it actually difficult to understand the spreading patterns and also to predict them. And then came big data, and Google said, we have a solution for it all. And they came up with Google Flu Trends. So basically what they did is they were looking into research requests of certain kinds, and they were taking the frequency of certain keywords that people were typing in, like headache or fever or whatever, as an indication for the seriousness of the flu or whatever was kind of circulating. And so you could basically do a nowcasting with some particular forecasting methods that are known from statistics, for example. One could even try to do some forecasting. Well, that seemed to work for some time. In fact, it was presented as one of the great success stories of big data. Then later on, actually, criticism came up, and even the service was stopped altogether. Do you have any idea what might have happened?
symptoms would also be attributed to stress and work environments related to stress. So industry patients with
okay, so ambiguity on the one hand, and then correlation is not causation. We have heard that as well. And, yeah, not sure how much Google cares about it. It's like, just make sure we vote, see the data that they have. I mean, now in the meantime, you can actually look into some of your own data at least. But what else happened? Does anybody remember Cambridge Analytica? What was that about? Yes? So it's at some point in time they were trying to influence people's decisions with personalized information. And that could be elections, but most of the time, of course, it would be about advertisement for products or services, right? So basically, if somebody types in headache, somehow, you know, an advertisement would flash up for pills against headache or whatever. And so going from observing or surveilling the world towards trying to influencing the world makes a big difference, right? We're basically destroying the measurement process. Just think of quantum mechanics, right? So cannot measure kind of location and momentum at the same time. So the measurement kind of changes the state of the system. And so here, the manipulation of people's decisions basically changes the state of the world, right? And so you cannot do both, have an accurate picture of the world and change it, you know? That seems to be one of the problems. We have also heard about the limits of predictability. Anyway, besides the purely data-driven approach that Google Through Trends had basically taken, there are other model-based approaches. And one of them is actually represented by what GleamWiz does. And here's a video from the times that we've been interacting with the team of Alex Espinal.
While devastating pandemics have so far been rare, today's high population densities and intense mobility increasingly threaten to push epidemics to pandemic proportions. The costs of such pandemics can be immense: countless fatalities, untold physical and emotional pain, soaring healthcare costs, and supply chain disruptions. Now, with Gleam, we can analyze how infections may spread globally and assess the best ways to minimize their impact. By combining epidemic models with real-world data. Gleam produces simulations of the global spread of infectious diseases by integrating 3 layers. The first layer looks at people and their geographic distribution with respect to major transportation hubs. The second layer adds data on the mobility of the people, how they commute and travel around the globe. The third and final layer adds the epidemic model, which can define complex disease scenarios and response strategies such as vaccination campaigns or emergency travel restrictions. Combining these 3 layers, Gleam simulates epidemic spread at a worldwide scale. The resulting forecasts and scenario analyses help inform on how best to counter pandemic threats. Visit gleamvis.org to learn more about Gleam.
I'm actually seeing this now. This movie is around the year 2012. I haven't seen it for 2-3 years, I guess. Seeing this now really makes me shiver a little bit because somehow that movie anticipated a lot of what was coming, right? Yes, and this is actually the most important thing to consider. So the GleamWiz is a pretty detailed model which is using a lot of data. It has a lot of parameters, and the issue really is that all of these parameters are only known with a certain accuracy, and little changes could sometimes have an impact. Think of the butterfly effect that we talked about. In comparison to that, Dirk and I have been developing a much simpler approach. And that approach basically doesn't work with big data, but instead it combines two data sets. Doesn't do just a data-driven approach. It combines two data sets and it takes on board some knowledge about how diseases spread. That means the science of disease spreading is incorporated into the model. So suppose you would have a world map or a globe where whenever somebody is catching the flu or some other disease, light would flash up. You would really see how a disease spreads around the world. Now, frustratingly, if you do this, you would not be able to make sense of how the disease spreads. And you see that basically in those very widely scattered data clouds over here. There's no clear correlation, right? Everything is messed up by air transport, basically. And so the idea that we had was to replace geographical distance by another kind of distance, which would be based on travel volumes between airports. Because that turns out to be kind of a key variable. And in this effective distance where New York and Frankfurt are close by, or Beijing and Tokyo are close by, or Paris and London. In this representation, suddenly you have, again, a diffusive spreading pattern. And it actually spreads in such a circular way if you know the origin of the disease. Now, actually, in many cases, you don't know where case 0, patient 0 has actually occurred. So do you have an idea how we could try to figure out where that has been the case? We basically look at the data from the point of view of any of the cities with an airport being the potential origin of the disease. And then we look for the most circular spreading pattern to identify the most likely origin of the disease. And once we have done that, basically, we can calculate into the future what would be the most likely cities to be hit or reached next by the flu or COVID-19 or whatever. So basically, you can take proactive measures. You can put more medical personnel, you can put more medicine. You can, to some extent, anticipate how the disease spreads. And now you see when you do that, a pretty linear, strongly correlated situation of the data points, which basically shows that now we can make sense of what's going on.
If I look at the situation, origin,
Yes, this is what you can try to do. Yes.
it's like it's change the distances and this something that is just the same way you change the origin of something that is if you
Yes, I mean, you hypothetically put any airport as the potential origin of the disease, but for most of the airports, the spreading pattern that has been found would not be circular at all. So basically, we could conclude that most likely that has not been the origin of the disease. So just to compare the two representations, the geographical on the right versus the distance, effective distance based on the left. And here we're doing the same thing with a different origin of the disease. And of course, these kind of analyses have also been done for Ebola and COVID-19 and for all the diseases that come up. Dirk Brockman is the first one to apply this methodology in order to get a picture of the risks that result from such a scenario. Now, what else can we do? Basically, there are different ways of collecting data. And one of these approaches is a participatory, crowdsourced approaches of collecting data called RipiNet, Related Services InfluenzaNet. And here people report anonymously about how they feel. And I would give an overview of the situation. And the idea is to provide a public service, some information system that would allow people to see what the situation in their city or canton is like. And they could basically take protective measures according to the situation. We've also at that time been thinking about vaccination strategies, but not a mandatory vaccination strategy, but an information-based strategy. So the question that we've been asking is, what kind of information do people need to have in order to be able to take reasonable, responsible decisions? So we were looking basically at the effectiveness of vaccination strategies independent of what is the radius within which you determine the disease situation and give feedback about that kind of situation. So you can imagine it's not very effective if I'm the only one who have a very local information. I'm the only one to be considered, because I would infect myself potentially from my neighbors or my colleagues or my friends, right? So if you take the circle too small, then the vaccination strategy would not be effective. The information would not be very useful for me, not useful enough. Same thing if you average over the entire world. If I live over here, I don't need to know what the vaccine, what the infection situation in Africa is right now or in India is right now. This is important for the people living there. I need to know what is the situation in my canton. So there is where I could potentially be infected. So in essence, there's a radius that determines the optimal information. That would determine what information is really relevant for me. And that's kind of the ineffectiveness of world news on TV. You know, there are always disasters happening in some place around the world. Most of them, fortunately, don't hit us personally. We would better have some information about anything that could be relevant for our own lives. Right? And this is about exactly the question of how to determine what kind of events we need to consider to give people relevant information. Obviously, there are important network interdependencies when it comes to spreading of diseases, but the same thing applies to many of the other phenomena that we'll talk about today. If we have network systems, then whatever you do would most likely not only have the intended effect, but it would also have side effects, in many cases undesired or unwanted side effects. It could be feedback effects, there could be cascading effects. And this is important to know. So a networked world behaves in a very different way from a world which is sparsely networked. And in particular, the cascading effects are those that are particularly dangerous. Not always, you know, innovation spreading is an example of a cascading effect that we consider to be positive in most cases. But many of the disasters that we see have some cascading effect as the mechanism that actually produces the disaster, amplifies the original cause, often by a factor of 100 or 1,000 or perhaps. Yes. So we are showing here a little simulation. Green is healthy, red is infected, and you see infected people infect other people in the neighborhood. But altogether, the system looks stable. Yeah, this is a simplified representation of kind of the Earth's surface. But what we want to show now is what happens if we have shortcuts. So people, for example, take the plane, travel to other places, and if you have some of those shortcuts, things are not that bad. It looks still similar to what we've seen before. But now you can imagine random shortcuts, yeah. In this case, without hubs. You see, suddenly things got totally out of control. And sometimes very few additional links can make the difference. All right, now at least you understand why we had the social distancing and the lockdowns, because if you're on this side of the graph, basically things are out of control. You need to get on that side of the graph. And this is, of course, what the political measures we're trying to do, so-called non-pharmaceutical measures. But for most people, it would probably be unexpected that there is such a sudden change in system behavior at a certain point. It's not exactly a tipping point because it's not discontinuous, but still it's still pretty steep. And many of the systems that we'll be talking about have this characteristics that one event would potentially trigger several further events that would again potentially trigger further events. So this is how the cascading effects would come about. On top of this, there's often non-linearity, there's often also randomness. That means the triggering of other events only happens with a certain probability and perhaps also with a certain delay. So these systems are very difficult to calibrate, to understand, to model exactly. There's basically an interplay between risk and complexity, and that creates uncertainty. So things could be very bad, but if you're lucky, you would end up okay. This makes it, of course, very difficult to give good advice to politics, right? And politics really had big trouble handling that uncertainty. They typically just want experts to tell them what they should do. And that comes down to determining a mean value that is representative for the system behavior. If there's large uncertainty, however, you need to consider the distribution of events. It could be really a widely distributed scenario so that there's large uncertainty and the mean value may not be characteristic at all. And particularly if you have a multimodal distribution, then the mean value tells you very little. And so that requires basically very flexible response strategies. This is a nice representation of cascading effect. So within a very short time, these cascading effects can mess up the entire system, and that could be the goal, unfortunately. Now, we are living in a world that is characterized by increasingly strong coupling and also by complexity. And these kind of systems behave fundamentally different from what we're used to in the past. There's faster dynamics in many cases, there's increased frequency of extreme events. Self-organization dominates the system dynamics with the emergent and counterintuitive system behaviors. Predictability would go down. External control is difficult, and the systems are largely vulnerable. So hopefully that was not the patient zero event. Next wave. So when it comes to the distribution, in many cases we don't have a normal distribution, but instead a parallel distribution. That means extreme events are much more frequent as compared to what you would expect according to a Gaussian distribution, a bell curve. Do you have a question or comment? No? So altogether, I think we probably agree that networking is good. Many reasons for it. You know, you have a global exchange of people, money, goods, information, ideas. All of that has advantages, but also those network infrastructures and interactions create pathways for disaster spreading. And if you saw the big data is going to save us, I would warn you, because on the one hand, data volume is increasing much faster than processing power. That means most likely we'll never process all the data that has been created in the first place. So there's dark data in a sense. You need to know what part of the data should be processed and how. And that's a tricky thing sometimes. And also systemic complexity is increasing even faster than data volume as you continue networking the world, because that grows combinatorially, not exponentially. So even though we have more data than ever and better technology than we've ever had, we tend to lose control of the world if we try to control it centrally. But I think we're basically seeing it now in many places. You know, it's climate change, the pandemic, supply chain disruptions, and all these kind of things. So this is now happening. We warned of that back in 2010. There were 12 years to prepare. I'm not sure how effective those preparations have been. It seems sometimes that those in power believe more in a centralized control approach. Apparently, we're now seeing that it has its limits. And so systemic instabilities do result or are connected with those cascading effects. And here's one of the book chapters that you might want to cover in your presentation. What we've done over there is we've really looked into many reports of disasters that have happened in the past. And I've tried to identify causal relationships. What event causes what? And then it turns out, even though there's a lot of chaos in these events, there's still some logic, because there's some physics behind it, for example. And so there are some causal relationships that also translate into temporal sequences. And if you know about this causality network, you can anticipate what will happen next, potentially. So even though you don't know exactly what will happen, you at least, or whether this will happen or not, at least you know what would happen in what order, and you can still do preparations. You can take proactive measures. And in fact, you should be doing it, because the most important thing when a disaster strikes is you should try to stop the cascading effect as early as possible, because this is what determines the size of the disaster. You have to be quick. You have to reduce the amplification. You have to stop the process. So we've done that for different kinds of disasters, in this case, thunderstorms, and it turns out there are also some common elements of disasters. So when there's a disruption of anthropogenic systems, there would often be blackouts that would have implications for the transportation system, but also for the telecommunication system, which would often also not work. And supplies would get short, and that would impact, would basically create black markets and all sorts of side effects that are not desired at all. And that one thing that you probably also noticed is if a disaster strikes, worse comes to worse. You know, the rescue efforts are delayed, or it's more difficult because of the storm, and all those things that had been planned to be done cannot be done because of very difficult circumstances. So worst comes to worst. For example, an earthquake could trigger a volcanic eruption, could trigger a landslide, it could trigger a tsunami, a flood. So these are the kind of things that all need to be considered. Now, another question that we've asked ourselves is, can you be better prepared? So we've not only been looking into the cascading effects, but also we have been considering that there are human and other resources that are deployed throughout the network in response to what is happening. And those activities would heal damage in the system. And then the question is, how should you actually deploy the resources that you have? It turns out that this depends, among others, on the network structure. And so you need to know your network. So if you're interested in this, you could have a look at that particular paper, so you can see the kind of different spreading dynamics depending on the network structure. Also, you could have homogeneous or heterogeneous networks. But one thing can be said for sure. The more delay you have in the deployment of resources and response capacities, the bigger will be the damage, the more costly will it be to recover. And in many cases, you know, the effort will just come too late. So immediate response is really crucial. And even it costs $1 million or $1 billion, you know, if you delay this process, we'll pay 10 times more, 100 times more, whatever. So green is kind of where things are still reasonably under control. Yellow is already quite bad, and red is kind of everything failed. So here you see different kind of networks compared. These are, I think, resources, and those are different strategies to respond. So you can clearly see that the most effective strategies depend not only on resources and time delays, but also on the kind of network. Here's some notes on this, so I don't think I have to read that. But perhaps one of you would want to present that. Now, of course, you want to have an operation of systems that is resilient to challenges, to disruptions. Systems that could recover also from disasters quickly. For that, you need adaptive systems, right? That means not unchangeable systems, but adaptive systems. Perhaps you still remember that cars a couple of decades back, if they had an accident, you didn't see much damage of the car, but the driver was often dead. And now, if a car has an accident, it often looks terrible, but the driver is still alive, you know, and in many cases, even the injuries are reasonably small. Because we have decided that human life is more important than the property of the car. And we should design the car not in a way that it would have minimum damage. On the contrary, we are using it as a buffer to absorb the energy to protect the human being. So we've gone from a car that was maximally unchangeable by an accident and maintained its shape, but the driver was dead, towards a construction that is maximum adaptable to protect the really valuable human being. And this is very important also to consider for all the systems that we design. They need to be adaptable rather than unchangeable. And actually, many of the systems that we have today are not yet of this kind. Digital technology will allow us to come up with more adaptable systems, but also we have to consider that communication could break down or systems might be hacked. All right, so there are certainly some drivers of systemic risks that we need to consider. Less redundancies to save money, you know, for sake of economic efficiency. More networking, higher complexity, faster dynamics, high pace of innovation. In case we don't know the side effects yet. But on the other hand, you can still increase systemic resilience by a number of mechanisms, by having backup strategies, redundancies, plans B, C, D, whatever. Now, when it comes to the financial system, for example, we don't seem to have a backup plan. That was always kind of puzzling me, you know. Why don't we have kind of 2, 3 parallel systems, so in case one of them fails, we still have another one taking over.
Local currencies, for example. Local currencies, for example.
Local currencies is in fact a very interesting idea, and the finance for system, if we still get to this point, probably not today. You could also download that book or talk about that. This is based on the idea of local feedback on local currencies using digital technology. Then you could try to simplify, limit system size, you could reduce connectivity, you could have dynamic decoupling strategies. Diversity is important because if there is failure, not all the system elements would fail at the same time. Real-time measurement and adaptive feedback, transparency and awareness, accountability, responsibility, suitable incentives, collective intelligence, and we could go on. So it's not like you can do nothing. On the contrary, but you need to consider that systems may fail. And if they fail, that's often very costly. It may be rare, but if it happens, then it's very costly. So you cannot just ignore it entirely. And you need to have a strategy, and particularly you need to be able to interrupt the cascading effects. I need a system that could actually adapt in a probably self-organized way. So as the complexity of the system increases, it turns out that some autonomy of control, like distributed control approaches, would often be beneficial to achieve the goals of that system. Okay, so to summarize a bit, diversity, decentralization, modular design, distributed control, subsidiarity are principles that make sense to increase resilience. And important point, perhaps trivial for some, but often ignored, is strengthening strong links does not help. It's always the weakest link that tends to break. It is not necessarily a bad thing to have a weak link. You can use it for something. In fact, in the electrical networks at home, we have built in those artificial weak links to make sure if there's a failure in the system, it would not create a big damage, but it would create a controllable damage in a place where it doesn't hurt much. Also, there's a change in the way disaster response is organized. In the past, it was pretty much done in a military way. It's a control center. The control center basically collects information about the situation, and then there's a military guy, perhaps even say a general, who then decides what needs to be done and gives commands to the lower levels, and those give commands to their lower levels, and then this is executed. But there's just so and so many soldiers and military people who can take care of the situation. And also it takes time to deploy the military into those places, and often days. Most people die in the first 3 days. The military often arrives after that. So basically, the only people who can help after a disaster, when in the first days when help is most critically needed, are the people who are in that location. So we should empower them to help themselves and to help each other. And in fact, with digital platforms, you can give them some means at hand that allow them to self-organize and to do exactly that. So rather than kind of this control and command system, we can have a system where people say what they need, and other people say, I can do this, I can do that, I can help, I can, And in fact, the very nice thing in disasters is that people are often extremely helpful. The main problem is often to get that help coordinated. But that can now be done much better with digital platforms. We create a local sharing economy, things like that. And so we have just written a paper, not yet published, about participatory resilience. Sachit is actually the first author. And here we have been looking into this situation of disruption, and the scenarios that people have been looking at most of the time was collapse, degraded recovery, and anti-fragility, where basically after the disruption, the system would get on a higher level, a better organization. It went so far that some people have started to say, if we want to improve the system, we need to have a disruption. So they were kind of almost inviting disaster to get to a higher level. But our point of view is that you could also get on a higher level by participatory approaches and by a co-evolutionary approach, where everyone is enabled, empowered to locally improve, and everyone responds to the improvement of everyone else. And so the system co-evolves to get better and better and better. We've also been thinking about innovation, upgrading schemes. Yeah.
Series of catastrophic events. And that
the classical view, I think, has often been that systems progress and history progresses through a sequence of failures and disasters and catastrophes.
It's like the phoenix that is born from the ashes.
Yeah. That is kind of the view that I've often seen. And what we are saying is, but if you take a participatory approach and a co-evolutionary approach, then perhaps we can overcome that never-ending series of disasters to make progress. We could make progress by many little improvements that respond to each other and lead to that co-evolutionary process that we also find in nature, in ecosystems, and so on. And we've also been thinking about upgrading systems. Experimentation is important to basically discover better ways of organization. So not all the experiments basically are better. Either they would happen on a small scale, those experiments, or they would happen in the virtual world. Right now we have the metaverse. Basically, we can make experiments over there to see whether there are some better ways of organizing things. And once we have identified such better ways, we would eventually have a change over to that kind of organization. We are just in the process of revising it. I guess in about 2 weeks we'll be there. Yeah, I mean, we do hope that it will change the perspective on how the world will evolve in the future. And this paper over here, that is already published, has been looking at situations where participatory fairness in emergency communication can support self-organization for survival. So basically, in many disasters, what happens is you need communication, but this is what breaks down. And then people basically stay without communication, and this is a very bad situation. But now with smartphones, you can basically produce ad hoc networks. And then the question is, how would you organize those ad hoc networks? And the point we have been making is that you should use the smartphones with the most battery charge as the relay station to basically transport the messages to other smartphones and eventually to the destination phone. And of course, then eventually their battery goes down. But at that time, then other phones would take over who still have kind of spare battery capacity. If you do that, then basically you can keep up the communication network for almost everyone. And that was the goal for about 3 days or even longer, to allow at least to do text messaging and to have kind of the most essential information go to the places where it has to go, so people still have some basic communication ability when they need it most. And it's very important that nobody gets lost. In a sense, nobody is left behind, because if somebody drops out, that creates holes in that communication network, and then it doesn't work anymore altogether, because you need to have enough phones in a close enough neighborhood in order to have the ad hoc network run at all. So basically, this fairness approach is something that keeps up the communication network for everyone and for a longer time, and thereby everybody is benefiting. So it strengthens the social fabric. It strengthens the communication infrastructure, but also the social fabric, that means the capacity to help themselves and to help others. And quite significantly, as you can see, so it's kind of a typical mesh network, and that's the system that we suggested instead. All right, coming to power grids. Now, since some time, people are talking about future blackouts. It's hard to guess why everyone is talking about this, even before people were talking about gas and oil shortages. But anyway, these blackouts have happened in the past already. One of those incidences was on November 4, 2006. And basically, it was a ship that had to be transferred, and electricity line had to be turned off for this. And on top of that, another line failed, if I remember right. So they had been looking at the impact of turning off this line, but they didn't expect that an additional line would fail. And as a consequence, we had blackouts in many places all over Europe, hundreds or even probably more than 1,000 kilometers away from each other. And that happens in a very short period of time. Here is a paper that somehow looks into some issues that can happen in power systems, because you have to synchronize the network. 50 hertz periodic network, right? And that all needs to be synchronized, and it can happen that there's desynchronization in the system. I can imagine that the network structure actually matters for where that will happen. We're also looking into cascading failures. In this case, for an electricity grid in the UK. And some researchers have basically used very simplified models where they assume that a certain line would fail. And then basically the load of that line would be redistributed over the remaining lines. And you could imagine that okay, now they would get overloaded and further lines would fail. And a cascading effect would set. What we have done on top is that we have considered basically that there would be these overshooting effects, some dynamical effects that would, as it turns out, make the electricity grid even more vulnerable to failures. So the dynamics also needs to be considered. In fact, cascading effects can be pretty surprising, counterintuitive in their nature. I often mentioned this counterintuitive nature of complex systems, right? So what we'll see over here is that that assumes scenarios simulated over here. This starts in Spain, and then for some time, it seems to go away. The problem seems to disappear. But then sometimes later, we'll see a really big blackout event in a very distant location. Okay. Disappeared almost. And now it gets really bad. So the non-local character of these phenomena is also very important. Right? This is a computer simulation, but the network seems to be based on a real network data. It shows you, however, you know, how many unexpected things can happen in these kind of networks. Right? And of course, the blackout is just the first thing, because what that happens is traffic lights are off, public and private transport is down, gas stations don't work, there would be disruptions of cellular phones, the wired phone network would be busy, pumps would not work. That means water could not be, it's not drinkable. You would have to boil the water, but how do you boil it if you don't have electricity, right? You don't have light, you would use candles. Some of those candles would cause fires with a small probability, but still, you know, then basically the firefighting needs to get to those fires, but hey, how do you get there if everything is congested? So you can imagine that a blackout is just the beginning of a series of other events that really create all sorts of nightmares.
There's one question.
Yes?
Isn't distributed power generation supposed to make energy supply more reliable? Where is the
Okay, this is a very good question. So in the past, electricity grids were organized in a national way largely. And then Europe was kind of created as a political entity. And that also led to shared markets that would span many countries, and also electricity networks would be grown together, but they would not have been planned as a European grid. And so basically, the grown together network was not the perfect layout for Europe. For historical reasons, you know, it hadn't been planned for that. So this paper over here is actually looking into the question, could we actually make the network more resilient by just changing a few lines? And in fact, it suggests that just a few changes in the connections of that grid could have a large mitigation effect. And then on top of this, today, of course, we have increasingly smart grids where not only the power generation is distributed, but also and adaptive, but also the consumption is very much adaptive. So the idea is that some of the power consumption would be scheduled at times where there's a lot of energy available. Like, your electrical car would be charged at night, the washing machine would run at night, these kind of things. Now we're getting towards another recent problem, the gas supply network. Here is a paper from the year 2014. Resilience of natural gas networks during conflicts, crises, and disruptions. Perhaps also a nice choice for one of your presentations. So here we have been looking at the European gas network. Difficult actually to get access to the data. And you can see basically the volumes and the network. And obviously, there's a lot of gas coming from Russia. Also, some of it comes from Africa, and some of it comes from UK, Netherlands, Scandinavian countries, and so on. Now, the question is, how can you handle different kinds of scenarios, including political scenarios? And there were basically 3 levels of data that we have considered: the gas network, the urban areas, and the population density. I can see basically who are the countries that export gas, and the other countries over here are consuming gas, and what goes where. This is liquefied natural gas. A lot of talking about it, which is delivered basically by ship. And then we have been considering, what if one of those countries is suddenly not delivering anymore? And see, here's Russia, here's Ukraine. A country is resilient to crisis if it combines high throughput per capita across scenarios with a low coefficient of variation of throughput. That means basically where things more or less stay the same. And we have been looking into all sorts of scenarios, and in particular, we have been looking into scenarios where there would be issues with gas deliveries from Russia or Ukraine. So if you want to know more, then I advise you to have a look at the paper and present it in detail to us. Okay? Energy supply is an issue altogether. And of course, there are many different kinds of energy supply systems, and all are somehow interconnected. To some extent, you can replace one kind of energy by another kind, but as it turns out, things are kind of tricky. We'd like to reduce the consumption of oil because it's carbon-based, it produces CO2, it has impacts on the environment that are not desirable, but if we would invest into nuclear power, then we know that there are some risk, as we've seen with, for example, Chernobyl and Fukushima. These risks apparently are not zero, and the impacts could actually be global, not just local. Okay, then people have been thinking about solar power, and there was the so-called Desert Tech Consortium. They wanted to invest $1,000 billion or even euros into an infrastructure that would produce a lot of solar power, largely in Africa, other desertous areas, and then deliver that electricity all over Europe. The gas supply, okay, we know is kind of politically sensitive. They were also trying to grow biofuels. And then what happened is, of course, the biofuel production is in competition with food production. I mean, food gets more expensive. If food gets too expensive, then there are revolutions. Suddenly there was the Arab Spring, and as a consequence, the Desert Tech Consortium gave up on its plans because things were political not anymore stable. So you see how everything is somehow connected with each other. Whatever you do has some undesired side effects, apparently, that produce problems elsewhere. So you're improving one thing, you're deteriorating other things. And apparently, until today, they don't have the perfect solution yet. Hopefully tomorrow. So that is kind of a generalized cascading effect. You know, whatever you do in the system, it has problematic impacts. So what time is it? It's 50 minutes. And we can talk also a little bit about supply chain disruptions. That's an issue that people now get concerned about. It's partly because of the pandemic. A lot of container ships have not been unloaded. There are a lot of delays. Not only is there a scarcity of chips for power production and so on, but also it's food could be falling short, some kinds of foods, and so we need to look basically into supply chains, and we've done that also many years back. Here's just one example of how difficult things can get. You know, when the new Heathrow terminal was opened, we started with big chaos. Because going from 0 to 1, kind of from no operation to full operation, is a kind of disruptive change. And they could only, as it turned out, gradually go from 0 to 1 and not from one day to the other. So like in the beginning, it was just a huge chaos. Not the kind of chaos we currently have in terms of shipping containers. And now, also worse comes to worse again, those containers are not available for other deliveries now. So there's a shortage of containers. Plus, not only would there be, as a result, a shortage of deliveries and goods, also there seems to be increasingly a shortage of workers who could, lorry drivers, for example, truck drivers, that could deliver. And so there were already news that were suggesting that the Russia-Ukraine war would actually ripple across Africa and Asia, far away. And here basically the countries that would be affected by the war between Ukraine and Russia. Nigeria, Kenya, Philippines, Myanmar, Morocco, Turkey, Egypt, Thailand, Indonesia, Tunisia. So if we complain about a shortage of certain kinds of oil in some European countries, apparently it's probably a small problem as compared to the problem that could occur in those countries. Now, let's look a little bit more into supply chains, because supply chains, again, are dynamical systems. And I learned that first in connection with a chip producing company, Infineon Technologies, when I was in Dresden. So they had companies to produce those wafers, silicon wafers, which eventually be turned into chips. And this is one of those so-called wet benches where the silicon wafers are put into different kinds of chemicals, one after another, in order to etch out the structures that would basically give the computer chips. And in between, you have to wash away the chemical in the water basin, okay? And these wafers are being transported by a unit which is called the handler. The handler basically moves things around. There is one of them. And there are many of those wafers. So it could happen that several wafers want to be transported at the same time, and then there's a conflict, okay? And then it could happen that one of them is prioritized, the other one has to wait, but perhaps it has to wait too long. So the chemical, has a damaging effect, and you have to throw away the wafers. But there's only a certain time period which is good for the process. And you have to stay within that minimum and maximum processing time. So if you prioritize another wafer, you could have delays that cause exceeding the maximum treatment. And those machines were delivered with certain throughput rates, and it turns out that they had difficulties to really reach the maximum throughput. I know producing kind of 5 or 10% more, it really makes a big difference. Easily you get into the millions of euros. Now, of course, the idea is let's run this process with different treatment parameters, combine different parameters, and see how well it works. And you make these measurements and you try to extrapolate what happens for parameters in between. But look what happens, there's this huge variability. So basically, if you know what happens for this parameter combination and just change it slightly, you can't predict what the outcome would be in terms of this throughput. There's a huge sensitivity. And so you could not interpolate this. So you see, this is what was promised to them. This is what they actually managed to produce, a lot less. Okay, so this is the process, just to give you a better idea. All right, so things are being moved around. Not a very complicated thing, but anyway. So what we then did, we created a software platform where the parameters could be changed. And what they have basically done before is, in order to increase the throughput, they were trying to shorten the treatment times. And I said, wait a minute. Ever heard of the slower is faster effect? That we knew from the pedestrians that we were studying at that time. And so the proposal that we made was kind of counterintuitive. We told them, you should extend the treatment times rather than shorten them. Because then you have less conflicts of interest between several of the wafers that wanted to be handled or moved at the same time. And see what happened. Basically, with our approach, more than 30% more throughput would be produced. They were totally happy with that. So we got to those numbers that they hoped to achieve. Slower is faster. Okay, so basically we got interested in logistics systems, and then we basically learned about the beer game. And in the beer game, you have a logistics system with different, retailers and distributors and wholesalers, factory and so on. And you basically find instabilities in a similar way as you have stop and go ways in traffic flows. And even managers would make those mistakes, it's just an instability that nobody can handle. Okay, so we've been looking into this mathematical wave, starting with supply chains, linear supply chains, and assuming that the stock level will basically change based on inflow minus outflow, obviously. And there would be delayed adaptations of the production rates. See, you're producing too much or too little, and then you adapt the production, but it takes a bit of time to adapt. And the delays often tend to amplify certain effects. So basically what you see over here, a little variation in the consumption patterns could actually produce large variations in the production system. Of course, that depends on parameters. As you can see over here, there's also an area where basically things are stable, but there's kind of too much delay, and basically things start to get out of control. And obviously, now we have these delays in the world economy, and that's to be feared that we would see these kind of effects increasingly. So now the question is, what happens if you have a network, not a supply chain, a linear one, but a supply network? Obviously, things get much more interesting. We've also been publishing a couple of papers about this, and in particular, we have been looking into different kinds of supply networks, different structures, a linear one, a hierarchical one, and what we call the supply ladder, with alternatives delivery paths. And here the dynamical patterns. So this is for the linear supply chain, this is for the hierarchical system, and this is for the supply ladder. So you can see the ladder with the alternative delivery paths can dampen out those oscillations almost completely. It's by far the best of those three systems. So from that point of view, perhaps it's not a surprise that Intel Technology had, based on their experiences, organized their supply network in a very similar way. They do have those alternative systems. Obviously, now it was not good enough to handle the disruptions that were in the world markets. And then we were looking into input-output networks. So you see here is a matrix which basically determines what kinds of materials go into the production of a certain other product. And so you have these input-output matrices, as they're called. And now things get really interesting because you could have three different kinds of situations. You could have an overdamped behavior, which basically implies that your economic system goes into an... Sorry, we had a blackout, battery is out. So basically, there's three situations. One is the damped exponential decay, which drives the system into equilibrium. Then there was a oscillatory damped solution, but it could also happen that there was a growing oscillation. And this is the thing that we need to be concerned about, because that would drive the system out of equilibrium and would not recover necessarily from disruptions, but instead we would have booms and recessions. And in fact, this is what has happened in the past, and that is also what is expected in this kind of situation. So large variations. Still, you know, if you have this kind of logistics data, you can make some predictions, and you can also figure out how that network could be reconfigured in order to make it more resilient to disruptions. And this is hopefully what will be the learning of the situation that we now are going through. Okay, so with this, we're anyway at the end of the lecture. I hope that was interesting, inspired you to take some more papers to be presented in the course. At the moment, the planning is that the presentations would go for 30 minutes and would be a 15-minute discussion, so we'd have 2 presentations in a day. In case a lot more students are signing up for presentations, we might go to 3 presentations in a day. That means 20 minutes presentation plus 10-minute discussion. But at the moment, we're assuming we would have a 45 minutes time slot for presentation plus discussion. And I'd really like to ask all the students to sign up for your paper and your subject and for a time slot as soon as possible, so we really get an overview of what's going to happen. Very much looking forward to your presentations, obviously, and this is going to start next week, so very exciting time. So now you're going to be in the center of interest from now on. All right, I hope you will have a great week and look forward to our next lecture in a week's time.